Jai Hind friends, I am Himanshu Tripa, Assistant Professor in Electronics and Communication Engineering Department at AKGEC Engineering College. Welcomes you all in my this session, and in this session we are going to understand how we can interface alphanumeric LCD displays with 8051 microcontroller. We'll see that what is alphanumeric displays or LCDs, and also we will see what are the commands or pins which are going to be useful in this interfacing with 8051 microcontroller, and we will write some code in assembly language to understand that how LCD is working. And to demonstrate you the interfacing of LCD, I have also prepared one Proteus based simulation. I will show you that how this LCD is connected with the microcontroller. About the circuit diagram we will discuss, and we will show you that how this code is running on LCD display. So, let us start with the alphanumeric LCD displays. Alphanumeric LCD displays are very common in embedded system projects or microcontroller based projects nowadays. They are common because of their low cost and their refreshing controller which is embedded onto that LCD panel. I mean that if I am buying any LCD from the market, it comes with a controller which is already connected or already available on the LCD panel. This controller is responsible this controller is responsible for the refreshing the content that is being displayed on the LCD device or LCD display. So, here on this slide I am showing you the very common LCD displays which we use in our projects. Here at the bottom with the green color, you can show this is a alphanumeric display. The specification of this display is 16 by 2. If I am saying 16 into 2 LCD display, what it means? It means that there are two lines of displays, and in one line we can display 16 alphanumeric characters. So, here you can see that in this last one green LCD display, there are two lines available, and in one line I can display 16 alphanumeric characters which I am showing you as A, B, C, D up to P. Similarly, we are having a 16 into 4 LCD display, and if I am saying that I am having 16 into 4 LCD display, that means I am having 4 lines on my LCD display, and in each line we can display 16 alphanumeric characters. Similarly, another common LCD display which we use in our projects is 20 into 4 LCD display, and the concept is similar like the previous one, that we are having 4 lines, and at each line we may be able to display 20 alphanumeric characters. Remember few points when we are dealing with LCD displays, that the number one is that we can only display the alphanumeric characters on these displays. Like the characters which are having proper ASCII code, we may be able to display only those characters on these LCD displays. But if we are thinking some innovative or we are doing something in the code, we may be able to display any character or any special character or any special graphics in bitmap format on these LCD displays, because for representing or for displaying one character on these displays we are having 5 by 7 dot matrix, like one character is being displayed in 5 by 7 matrix area. So, these are the few common LCD displays, and these displays we are going to connect with 8051 microcontroller, and we will see that how we can program our microcontroller to run or to display anything on these LCDs. Here I am showing you the pin diagram or the pin information of any LCD display. It does not matter whether we are using 16 into 2 or 16 into 4 or 20 into 4. we may be using any display, but the pins are going to remain same if these are alphanumeric LCD displays. So here I am showing you the LCD display pins information. We can see here that we are having displays like DB0 to DB0 to DB7. These are the pins. Let me use the pen. These are the pins available on my LCD display, like from DB0 to DB7. These lines are basically known as, collectively known as, the data bus for our display. So we can say that we are having 8-bit data bus with our LCD, and whenever we are transferring any character or we are trying to write any command onto these displays, we may send these commands or data into the 8-bit data format. And it is good to say that our microcontroller in this scope is 8051, and which is also a 8-bit microcontroller. Very easily we can output the 8-bit data. This is the simplest way of interfacing LCD with any microcontroller. But for practical use, because if we are using 8 data lines to interface a microcontroller, and if in our project there may be some more devices which we need to connect with the microcontroller, then there may be a pin crisis. To avoid this pin crisis, we can send data or we can transfer or write data onto the displays in 4-bit format. So for writing data into the 4-bit format, we have to do certain manipulations with the data, and that is the packed BCD and unpacked BCD manipulation I am going to talk about. But here in this text, in this video, we are not going to do the 4-bit LCD interfacing. We are only intending to do 8-bit LCD interfacing. So these are the data lines. And as we all know that LCD display doesn't have any glow of itself. So in order to make it visible in the night or in the dark room, it is advisable that we connect a back LED with all of these LCD displays. So one back LED is already connected with these displays, and this LED connection pins are available here, like LED plus and LED minus here. So you can say LED plus is LED anode and LED minus is LED cathode. So if we are providing plus 5-volt supply and we are providing at LED plus pin, and we are providing ground at LED minus pin, then this back LED will turn on. And if we are turning on this black LED back LED, then we may be able to see the content on the display in the night also. To control the operations for the LCD, we are having these 3 pins like RS, RW and EN. RS stands for read register select, RW stands for read or write, and EN stands for enable. These 3 pins are responsible to control the operations of the LCD. And to provide the power supply to the LCD, we are having these 3 pins. These are ground, VCC and VEE. So ground is intended to connect with the ground, VCC is connected with the plus 5-volt supply, and VEE is intended for to maintain or to adjust the contrast of this LCD display. So in order to adjust the contrast, we are going to use a variable resistor or pot, and we will connect the center pin or the jockey of the pot with this VEE pin, and that will create a potential difference, and according to the potential difference, the contrast of LED is going to change. So this is the information about the pins of LCD. Here you can see the detailed reference of these LCD pins. So now let's talk about more about the RS and RW and E. E is enable. RS stands for register select, and when we are talking about register select, every LCD is having 2 types of register. One is command register and another one is data register. So in order to operate the LCD, we need to send certain commands which will define that how this LCD is going to work, and these commands are going to be stored in the command register which is available inside the LCD. If we are sending any data that we want to display on the LCD display, then we can store that data, or we can send those data bytes into the data register which is already available inside the LCD. While we are doing programming, we need to select command register or data register. If we are sending command, then we can select command register by writing while writing 0 at this register select pin. So if my register select pin is connected with 0, then we can write anything into the command register. And if we want to write something into the data register, we can put this RS pin at higher logic or logic 1 or plus 5 volt. So this is a way how we select the registers available inside the LCD. Next thing is what kind of operation we are going to perform. Most of the time when dealing with these LCDs, we are performing write operation. We are writing certain commands into the LCD so that we can control its operation, or we are writing some data into the LCD so that we can display that data or those characters on this display. So most of the time we are involved in writing of the LCD. So read write pin basically signifies the type of operation, whether we are doing read or write. So if we are doing write, we can connect this pin with logic 0 or ground. There is one special case, that is the accessing of busy flag of LCD. So in case we want to access the busy flag status that is available inside the LCD, we are reading the LCD, and if we are trying to read the LCD, then we need to put this RW pin at logic 1 or plus 5 volt. So if this RW pin is at logic 1, we can read the LCD content, or while I am saying we are reading the LCD content, I am very specifically saying that we want to read the busy flag status of the LCD. And most of the time when we are writing something, whether it may be a command or data, we can put this pin at logic 0. The next important thing is enable pin. Enable is a trigger point. For example, if we want to write something on the LCD, it may be a command. So first thing, we will put that command onto the data bus. I can write it here as CMD. We are writing the command onto the data bus, and we are selecting this RS pin as 0. We are selecting this RW pin as 0. If RS is 0, that means we are selecting command register. If RW is 0, that means we are intending to write something inside this LED. But this write operation will complete only if the signal available at EN goes from high to low. This high to low transition is important. Whenever we are trying to write anything into the LCD, then we need to make this high to low transition at this enable pin. So this is the basic rule of the pins available with the LCD. Now let us talk about the commands which are available for alphanumeric LCD. Majorly these commands are used with 16 into 4 or 20 into 4 or 16 into 2 displays. Here is the list of these commands. These commands are available into the hexadecimal number system, and you can easily find these commands with the data sheet of your LCD. Like if we are sending command 01H, then we mean to clear the display screen. If we are sending the command 02H, that means we want our cursor to return home. If we are sending 04H, that means we are decrementing cursor, like we want our cursor to shift left by one position, and 06H for the incrementing cursor, like shifting cursor one position right. So these are the commands that we need to send into the LCD, and according to those commands LCD functionality will be set. Important commands are 38H. 38H command basically enables our LCD, and it enables both lines. Two lines LCD are available, and for one character display 5/7 matrix is going to be enabled. So almost in every project, almost in every code, we need to write this 38H command into the command register of display. Another important thing is the address of both lines or address of characters available on both lines. So here are two addresses, 80H and C0H. So first we will talk about 80H. So if we are drawing one LCD register, this is character 1 position, this is character 2 position, this is character 3 position, and so on. The address of first character in first line is 80H. So if we want to display our character in the first line and the first position, then we need to give the address 80H. Similarly, if we want to write or display our character at the first position of second line, the address of first character in second line is C0H. And what about the addresses for the second character and third character and fourth character? You can count in the sequence, like the 80H is the address of first character, 81H is the address of second character, 82 for third, 84 for fourth, and so on. Similarly, C0 is the address of first character of second line, then C1 is the address of second character of second line, then C2, then C3, then C4, and so on. So when we want to display any text or any string or any message on our LCD, we need to specify the address, and along with the address, if we are setting up increment cursor command, that means first character of the string is going to be displayed on 80H, then the second character is automatically going to be displayed at 81H, because we are forcing cursor to move shift right by one position. So there is no need to give address command for each and every character. If we want a gap or we want to put any character at a specific place, then these commands are needed actually. So these are the few commands which can be used while we are programming the LCD with 8051 microcontroller. So now it's time to write an assembly language code, and in this code we are going to interface 16 into 2 LCD with our 8051 microcontroller, and definitely we are going to use some assembly language. So let me shift here, and in my Keil microvision, let me open the code for you. So this is the code. Let me make it some bigger size. So this is the code, and I'll explain you the code line by line, and so that easily you can get that what we are trying to do and how we are basically controlling our LCD display. The first line of our code is org000h. It is an assembler directive, and the meaning of this assembler directive is origin. And if we are giving address 0000h, that means we are forcing our microcontroller or assembler to start writing code from memory location 0000h, like the very first memory location available inside the program memory of 8051 microcontroller. So the next instruction, the first instruction of our code is move a comma hash 38h. Remember 38h is an LCD command, and this command means that we want to initialize LCD 2 lines and 5 by 7 matrix for each character display. So this is the command. We are moving this command into the accumulator register, and we will transfer that content of accumulator into the respective port where we have connected the LCD. To write the command, we need to follow certain procedures, like we need to select the register select pin, we need to select the appropriate register using the RS pin. We need to put RW pin with at 0, logic level low, and we need to make a high to low transition at enable pin. Then only any command will be written inside the command register of LCD display. So to perform these actions, I have created one subroutine, and this subroutine I am calling here, and I am naming this subroutine is CMD write, that is the abbreviation of command write. So the first thing that I am doing, I am moving the command into the accumulator register, and then I am calling a subroutine which is responsible for writing the command into the command register of LCD, and this subroutine is CMD write. I have used instruction absolute call command write. Remember, absolute call is a call which can go up to the 2K memory location. Like the subroutine can be stored in the range of 2 kilobyte of memory from this instruction. After that, I am calling a delay. This delay is used for synchronization. As we all know that in any of our project, if there is one microcontroller and other peripherals which are connected with this, microcontroller is going to be the fastest device on this particular board, and all the other peripherals may be the slower devices comparative to microcontroller available on the board. So let's consider that LCD is a slower peripheral respective to microcontroller. So if microcontroller is sending a command and it is intending to store that command into the command register, LCD may take some time to store that command into it. And if in the meantime we are again issuing or again trying to write another command, then first command may get overwritten or it may get destroyed or haphazard. So to avoid this situation, we are giving some time to the LCD to cope up with the speed of the microcontroller, and this time is basically represented here in the form of a subroutine, that is delay. So what we are doing, we are issuing a command, we are trying to attempting to write a command into the LCD, and we wait for some time, and we hope that in this particular time LCD can easily store that command into its command register. Again, after that time, we will issue or we will try to write another command, and again we will wait for some time. This wait may be longer. This wait, you can say that it can decrease the performance of my code, but this is the simplest way available that how we can cope up with the slower peripheral in our embedded system or microcontroller based systems. So first command we have successfully written into the LCD. Like this, I am writing another command, that is 0EH, and this command means display on and cursor on. Like your display will be on and your cursor will be on, and it will be visible onto the LCD. So the same procedure I am adopting, that I am moving this command into the accumulator register, and I am calling one subroutine to write this command into the LCD. This subroutine is known as command write, and we are again calling delay to synchronize the LCD performance with the microcontroller performance. The next command I am giving 01H, and this command means to clear the LCD. Whatever is written on that LCD, it must be removed, and the new content that we are going to provide through our program, that new content is going to be written on that particular display. The method is same: issue the command and store the command into the accumulator register, call the subroutine command write, and call the subroutine delay. The next command is 06, that is shift cursor right. So whatever wherever we are going to store the first character, next character is going to be displayed onto the next location into the right hand side. So we want to write the first character of my message at 84H location, and 80H is the address of first character, then 81, 82, 83 and 84. Like we want to start the display of our string or character from the fifth position in the first line. Again, we are writing that command into the LCD. Remember one more thing, there is no rule to send these commands in a proper sequence. You can send these commands in any sequence, or if you believe or if you need, you can send these commands after sending the certain data bytes. So, to display the first data byte, certain commands are needed, but if in between you want to change the line, then you can again issue the command and again you can send the character, then those characters will be displayed on the second line. So, there is no proper sequence of sending these commands. You can change the sequence. There is no rule that first we need to send 38, then 08, then 01 or 06. No, you can first send 0E, then 01, then 06, then 38, then 84. So, you can change these commands sequence as per your wish. So, I have sent all the commands to the LCD. Now, it is time to write the data bytes. In this program, I am trying to write 1 byte at a time. So, I am transferring the ASCII code of character A, capital A, into the accumulator, and for that purpose I am writing this instruction, that is move A comma hash inverted commas A. Remember, this is immediate addressing mode and we want to send the immediate value of character A ASCII code into the accumulator. So, that is why we are using this hash sign here. Again, for writing the data, we need to enable the data register, then we need to put RW pin at 0 and we need to make a high to low transition on enable pin. So, to perform these actions, I have written another subroutine and that subroutine is basically known as data write, DTAWRT. So, I am calling this subroutine will basically write the ASCII code of this character A into the data register of LCD. In the similar fashion, I have written the ASCII code of K, then G, then E and then C. So, I have written my message onto the LCD. So, if everything is going right, then my message is now has been started on the display and I may be able to see the AKGEC on my LCD display. But we need to hang up the microcontroller, or we need to stop the microcontroller, or we need to engage this controller into some task. So, to engaging this microcontroller, I am putting an indefinite loop, and for creating indefinite loop, I am using unconditional jump. I have written S jump again and put that again label with this instruction only, so that continuously this instruction which is written at line number 32 is going to be executed forever. So, this completes our code. Now, let us see that what we have written inside the command write subroutine, inside the delay subroutine and inside the data write delay subroutine. So, the first subroutine is command write. See, one more thing here, that I have stored my subroutine just after the program. I am not using another similar directive of org. If I wish, I can change the location. I could change the location of this command write function, but I thought that it's okay to store the code into a proper sequence or into the proper memory locations. So, again the command write function involves, I am putting the content of accumulator into the port P2. I have connected the data bus of my LCD with port P2. So, I am putting that content of accumulator, it may be command, it may be 38H or it may be 01H or 06H or maybe anything. So, I am putting that value into the port P2 of microcontroller. Then as per the rule, I need to clear the RS, or I need to put RS at low logic, and RS pin is connected with P1.0 pin. So, I am clearing this P1.0 this will make RS0 for me, and my command register is selected. Then RW is equal to 0, and RW is connected with P1.1 pin. So, I am clearing this pin also. CLR P1.1 will put RW pin at logic low. Then I need to make a high to low transition at P1.2 pin, which is connected with enable pin of LCD. To perform the high to low transition, what I am doing, I am setting up the bit P1.2 so that it will become at logic high, it will become 5 volt, and I am waiting for a certain time, and for the wait I am calling again the delay function A called delay, and then I am clearing that same pin, that is P1.2 I have cleared, and now it is at logic 0. So, in this manner I have created high to low transition at P1.2 pin, and this pin is connected with enable. So, I can say that I have created high to low transition at the enable pin of LCD. Then if it is a subroutine, then our program control must return back to the main program, and for that purpose I have written RET instruction, that is the return instruction of this subroutine. Another subroutine that we have used is data write DTAWRT, and in this subroutine again I am writing the content of accumulator into the data bus of my microcontroller of my LCD actually. So, I have used instruction move P2 comma A, then set bit P1.0, because this time we need to put RS pin at logic high, because we need to select the data register. So, in order to select the data register, the pin connected with RS is P1.1, P1.0 sorry, and we are putting this P1.0 pin at logic high, and for that purpose I have written instruction set bit P1.0. Then we are going to perform write operation. So, we are making P1.1 pin is 0, because it is connected with RW pin of LCD, and again the same method we are using to make high to low transition or on the enable pin. So, to making the high low transition, we are setting up bit P1.2, we are calling a delay subroutine, and then we are clearing the P1.2 pin. And the last instruction of this subroutine is return, that will return back the control to the main program. The last subroutine that I have used in my program is delay subroutine. So, in delay subroutine I have basically created nested loops, and for creating nested loops I am using two registers of RAM, and these registers are R3 and R4. I am putting one value 50, 50 is in decimal. So, I am putting this value into the R3 register, and I am putting some value 255 into the R4 register. Then I am decrementing the R4 register and comparing it with 0. If it is not 0, then it will jump to here, and here is this label. So, this instruction is going to execute for 255 times, because R4 value is 255, and every time it will be decremented by 1, and certainly it is not 0, then it will come back to here, and again it will implement the same thing. When R4 will become 0, we are coming here at DJNZ R3. Here we are decrementing R3 by 1. Remember, R3 is 50, then after the first decrement it will become 49, and we are jumping at here 1. At here 1 we are again loading R4 with 255, and again we are executing this instruction for 255 times. So, I can say that in this way this entire loop is executing for at least 255 into 50 times. This is the way that how we can create the nested loops to generate delays in 8051 microcontroller. So, it is a subroutine, it will end with a return instruction, and last end assembler directive is showing that there is no more code available after this particular line. So, you have seen that how we have written the code for LCD interfacing with 8051 microcontroller. Let us quickly compile this code, to quickly build this code, not the compile, because we are using assembler, we cannot use the term compilation. So, let us quickly build this code, and now the code is built, hex file has been created, and luckily we have find 0 errors and 0 warnings. So, my code seems to be right. Now, let me show you the simulation that I have prepared on Proteus. In this simulation, in this simulation, I have basically created a very minimal circuit diagram for 8051. So, I have created one crystal, and the value of this crystal is 12 megahertz. I have connected two wave shaping capacitors with this crystal, and these capacitor values are 33 picofarad. Now, these capacitors are connected with ground, and the crystal pins are connected with pin number 19 and 18. You can create reset circuit here also, but since it is a simulation, we can do a power on reset. So, I decided not to draw the reset circuit here. As you can also see that there is no VCC and ground available. By default, this IC is getting the VCC and ground signal, and this is 8089C51 IC. Here it is visible that it is 8089C51. It is a 8051 compatible microcontroller, which was developed by Intel, which was developed by Atmel company, sorry. And here we will see about the connections of LCD. So, this is the LCD connection. Sorry. We can see that on the LCD, we are having the data bus of LCD from D0 to D7. I have created the labels, I have created the wires and put the labels on those wires. Like this wire is D0, then D1, then D2, D3, D4 up to D7, and I have connected these pins with the P2 port of microcontroller. P2.0 is connected with D0. So, you can assume a physical connection from this D0 to from this D0, and similarly you can assume a physical connection from P2.1, that is D1, to this D1 pin. So, this is the data bus connection for the LCD. I have connected my LCD data bus with port 2, and this is the contrast connection like I have discussed earlier. The first pin is VSS, that is connected with ground, and the VDD is connected with ground also, and VEE let me correct it. With VCC and VEE for the contrast, and it is connected with 5 kilo ohm resistance. Okay, we can change the resistance value by using these icons. The next thing is the connection of control signals. Here we are using RS, RW and E, and RS is connected with the P1.0, RW is connected with P1.1 and E is connected with P1.2. So, this is the connection and I hope that I have used the same connections in my code. Let us try to upload the code into this microcontroller. First, double click on this microcontroller, and from here select the proper hex file. So, this was my project, and here 04lcd.hex file that I have created using the assembly language code. Let me open this hex file. The clock frequency is 12 megahertz. Rest of the things are okay. I am pressing on this OK pin, and let me run this code. So, here you can see I have run this code, and this AKGEC has been printed on the LCD. Here you can see this is the cursor, and I have not issued the command for cursor blinking. So, that is why it is stationary, and this is the way how we can interface LCDs with our 8051 microcontroller. So, thank you guys for listening, for watching this video, and I hope that in the same series I will be presenting more such interesting examples or more such interesting codes and the interfacing problems with 8051 microcontroller. Till then, stay safe, stay happy, and Jai Hind.